The next stage is continuing with non-homogeneous equations to look for the particular solution rather than just the general solution. Just like for homogeneous equations, when we have a differential equation accompanied by additional information in the form of conditions, just like for a homogeneous equation, once you've got the general solution, you can use this information to find the value of any constants and to end up with the particular solution. One important thing to note, however, is you must use the whole of the general solution to find the constant and therefore the particular solution, not just the homogeneous solution. There's no point in trying to apply the conditions on the basis of the homogeneous solution and then adding in the particular integral. You'd then destroy those conditions that you had created. It is a case of find the whole of the general solution and then apply the whole of the general solution. So let's see some examples. In this first example, we're given what the general solution is. Here is our equation. Y is a function of t. We can see we have a polynomial right-hand side. We have the general solution here, involving an exponential and sine and cosine terms, and a particular integral of t. This is the general solution, but we're asked to find the particular solution satisfying the two conditions here, that when t is equal to 0, y is 1, dy by dx is minus 6. So we want to use this information to find the values of p and q. So here's our equation, along with the general solution and the conditions that we want to fit. So let's look at the first condition here. When t is 0, y is 1. So y is 1. E to the minus t, well, that's e to the 0, which is 1. And the bracket now becomes p times the cos of 0 plus q times the sine of 0 plus 0. So all that tells us the value of p. P is equal to 1. We've found one of our conditions, one of our constants here. The second condition involves the derivative. So let's differentiate the general solution. So dy by dt, we will have here a product to differentiate. So minus e to the minus t times this bracket plus e to the minus t times the derivative of the bracket here. So we'll get minus 2p times the sine of 2t plus 2q times the cos of 2t, plus, of course, the derivative here, derivative of t, is equal to 1. Here is dy by dt. Let's now to apply the condition here. Y dashed of 0 is equal to minus 6. So minus 6 will be equal to minus e to the 0, so that's minus 1, times, when t is 0, we'll get p plus 0, and then we'll get 1 times minus 2p times the sine of 0 plus 2q times the cos of 0 plus 1. So tidying up the right-hand side, minus 6 is minus p plus 2q plus 1 minus p will be minus 1. So the minus 1 and the 1 will cancel. We'll be left with 2q. 2q is minus 6. Q is equal to minus 3. We've found both the constants. So the particular solution, y particular solution, we take our general solution, we found p, and we found q. So we get here e to the minus t, 1 times cos of 2t, plus q, which is minus 3, times the sine of 2t plus t. So this satisfies the original equation, and it satisfies the two conditions. Let's have a look at another example here. Now this time we're not given the general solution. We'll have to find the general solution as part of our procedure. Again, y is a function of t, trig terms, and two conditions. Once more, one on the function, one on the derivative. So our equation here, along with the conditions. We need to start from the beginning, that is, find the general solution. Finding firstly the homogeneous solution involves the auxiliary equation. M squared plus m minus 2 is equal to 0. Well, it factorizes. Factorizes involving a 1 and a 2. So m minus 1 times m plus 2 gives us the minus m plus the 2m here. So we have two values. M is going to be minus 2 or 1. Two real, distinct solutions. So we can write our homogeneous solution. That is one constant, we'll call it p, times e to the minus 2t plus q times e to the t. Homogeneous solution. Of course, we've not considered the right-hand side. We need to do that through the particular integral. So let's look at the particular integral. We need to satisfy a sine and a cosine here. So let's try y is equal to some constant a times the cos of t plus another constant b times the sine of t. Now at this point, let's just draw attention to the difference between the p and q and the a and b. The homogeneous solution and its contribution to the general solution will be true for all values of p and q. And it's only once we consider the conditions we'll find specific values for p and q. A and b, well, only for particular values of a and b will the equation be satisfied. So we are going to find those values of a and b. We will need the derivative. Dy by dt will be minus a sine t plus b cos t and the second derivative, d squared y by dt squared, will be minus a cos t minus b sine t. We put all of this into the original equation. So what happens to the equation? The second derivative, that's minus a cos t minus b sine t, plus the first derivative, so that's minus a sine t plus b cos t, minus twice the function, minus 2a cos t minus 2b sine t. That's going to equal the right-hand side, minus 13 cos t minus sine t. And of course we see we get a little bit of reinforcing of the terms in a cos t and b sine t. So we can actually write that minus 3a cos t minus 3b sine t minus a sine t plus b cos t, that is equal to minus 13 cos t minus sine t. This is something that should be true for all t. It's not about finding t. We can compare the cosine terms, we can compare the sine terms. It should be true for all t. If we, for example, set t equals 0, the sine terms would all disappear. We'd be comparing the cos terms, and so on. So, looking firstly, say at the sine terms, what do we have involving sine t? We've got minus 3b of them, minus a of them, and we get minus 1 here. Minus a minus 3b is equal to minus 1, and we can call this one equation 1. As far as the cosine is concerned, minus 3a plus b is equal to minus 13. So transfer this one over to here. And that can be called equation 2. And then two equations in a and b. If we were to, say, take equation 1 and add 3 times equation 2, minus a minus 9a, so we get minus 10a. We'll get minus 3b plus 3b. The b's cancel. That was the intention of this particular combination here. We'll get minus 1 minus 39. So we get minus 40. A, we can see, is equal to 4. And then looking at either of the equations here, minus 4 minus 3b is minus 1. We get that b is equal to minus 1. We can use the second equation to check this. So we have the values of a and b. We can write down the particular integral. Y pi. Well, here we have it, a cos t plus b sine t. So we get here 4 cos t plus minus 1 sine t, 4 cos t minus sine t. And then, of course, that takes us to the general solution. Remember, the general solution is the sum of the homogeneous solution here. That's pe to the minus 2t plus qe to the t. We add on the particular integral. So here we have the general solution, pe to the minus 2t plus qe to the t. That was from the homogeneous solution. And then we add on the particular integral here. We've got the general solution. So now that we've found the general solution, we can then look at applying the conditions. The first condition, when t is 0, y is equal to 3. So putting this in, t is 0, the two exponentials will both be 1. So we'll have here that 3 is equal to p plus q plus 4 minus 0. So we get here p plus q is equal to minus 1. This could be called equation 3. Our second condition applies to the derivative. So dy by dt minus 2p e to the minus 2t plus q e to the t minus 4 sine t minus cos t. So applying the condition that when t is equal to 0, this is equal to 4. Exponentials, of course, still equal to 1. So we'll get minus 2p plus q minus 0 minus 1. So indeed here, minus 2p plus q, that will equal 5. And that can be equation 4. Well, if we subtract equation 3 minus equation 4, p minus minus 2p, that gives us 3p. The q's obviously cancel. Minus 1 minus 5, that is minus 6. So p, it turns out, is minus 2. P plus q is minus 1. So we get that q is equal to 1. And indeed we see the second equation is satisfied. So now we're finally in a position to write down the particular solution, take our general solution, put in the values of p and q. So y ps for particular solution minus 2 e to the minus 2t plus 1 times e to the t plus 4 cos t minus sine t. This satisfies the original equation and the conditions.